The computer, a device that has achieved unparalleled ubiquity, remains equally transformative in its impact on society, from the primitive tools for basic arithmetic to modern-day supercomputers and data centers. Most people are somewhat familiar with the important inflection points in the story of the computer. They know that during the Second World War, Alan Turing worked on a machine for deciphering the messages of the Enigma code by the Germans. Most people also know that prior to that he wrote a paper on computable numbers, which played an important role in the design of the aforementioned deciphering machine. What most people don't know, however, is that the machine which he outlined in this paper, the so-called universal computer or Turing machine, was later picked up by another of the pioneers of computer science, John von Neumann, to be generalized to something he called the universal constructor, the subject of this video. To understand the universal constructor, we first need to understand the universal computer. In the Turing model of a computer, there exists an infinite tape divided into cells, each of which may contain a symbol taken from a finite set of possible symbols. Moving across the tape is the head, which has the ability to read, write, and erase the symbol that is currently in view of it. The head executes instructions, which, given its current state and the symbol which is read, tell it what its next move should be. This machine is said to be Turing complete, or that it can simulate any computable function. Later, the design of the universal computer was taken by John von Neumann and recontextualized under his famous von Neumann architecture. The von Neumann architecture separates the computer into a memory unit and a processing unit, which correspond to the tape and the head in the Turing model. What von Neumann figured out, however, is that you can store the instructions inside the memory itself, inventing the concept of a stored program computer, the backbone of all computer software. The universal constructor was later born from the idea to build a machine which could not just simulate any computable function, but replicate any constructible system. According to von Neumann, such a machine would need to float inside a medium full of basic parts, which it could pick up and reassemble into a certain specified structure. The constructor still needs a tape or memory to store the instructions which are fed in, which tell it what to do. These instructions act in a sense as a template for the object to be constructed. The constructor also needs a memory control unit and a constructing unit, the latter interacting with the tape via the former. For this constructor to be universal, however, it must be able to replicate any specified system which can be constructed within the medium, including itself. For the constructor to replicate, it requires there to also exist a universal copier, which can take any description of a system X, call it phi of X, and consume it to produce two copies of this description. Then the universal constructor will take one of the copies phi of X and consume it to produce X. The result is X plus phi of X. If X is the complex of an alternating constructor and copier, we would have an autoreproductive system. In thinking about how this could work, von Neumann began working on a theory, the theory of self-reproducing automata, which he sadly never completed before his death in 1957. He did manage to do a lot, however, and indeed proved the logical feasibility of such a machine. In his work, von Neumann started out by asking 5 main questions. Question A. Logical universality. Can any single automaton perform all the logical operations which are performable with finite but arbitrarily extensive means? Question B. Constructability. Can automata be constructed by other automata? Question C. Construction universality. Can any single automaton construct every other automaton? Question D. Self-reproduction. Can any automaton construct copies of itself? And question E. Evolution. Can the construction of automata by automata progress from simple automata to increasingly complicated automata? In trying to obtain answers to these questions, von Neumann considered 5 models of self-reproduction: the kinematic model, the cellular model, the excitation threshold fatigue model, the continuous model, and the probabilistic model. For the first question, idealized neurons of the type studied by McCullough and Pitts were adequate to handle the purely logical functions of automata, but construction requires organs which can perform those non-logical functions which are required for the acquisition and combination of the organs of which the constructed automata are composed. In his kinematic model, von Neumann initially introduced as elementary units neurons a muscle, entities which make and cut fixed contacts, and entities which supply energy, all defined with about the same degree of superficiality with which the formal theory of McCullough and Pitts describes an actual neuron. The kinematic model then steered towards dealing with the geometric kinematic problems of movement, contact, positioning, fusing, and cutting, but ignored problems of force and energy. In total, the primitive elements of this kinematic model were of the following kinds: logical, switch, and memory delay elements which store and process information, girders which provide structural rigidity, sensing elements which sense objects in the environment, kinematic muscle-like elements which move objects around, and joining or welding and cutting elements which connect and disconnect elements. Stimulated by Stanislav Ulam, von Neumann decided to avoid the kinematical aspects of self-reproduction so that he could concentrate on the logical combinatorial aspects of this topic. He was thus led to work with a space in which the distinction between rest and motion is replaced by a distinction between quiescent and active states. Von Neumann then put various restrictions on this space. He wanted to have a high degree of regularity. He required functional homogeneity, isotropy, and selected a two-dimensional space. Because of the difficulties of working with a continuous Euclidean space, he decided to work with a discrete, crystalline space. This was von Neumann's second model of self-reproduction, his cellular model. In the cellular model, self-reproduction takes place in an indefinitely large space which is divided into cells, each cell containing the same 29-state finite automaton. Each cell communicates directly with its four contiguous neighbors with a delay of at least 1 unit of time. An infinite cellular automaton consists of an infinite cellular structure together with an initial cell assignment. An initial cell assignment is a finite list of cells together with an assignment of a state to each cell of the list. All cells not in the list are assigned the unexcitable state. An initial cell assignment determines the state of an infinite cellular automaton at time 0. The history of the infinite cellular automaton is then determined by the transition rule, which gives the state of each 29-state finite automaton at time t+1 as a function of its own state and the states of its four immediate neighbors at time t. Von Neumann decided to model the growth of neurons, or excitable cells, by the transformation of exciting unexcitable cells into excitable cells by the use of special stimuli, i.e., those that aren't reserved for the logical functions. Next, von Neumann referred to the constructing and constructed automata as the primary and secondary automata respectively. A description of the desired secondary automata is to be given to the primary automaton. Since there is no bound on the size of the secondary to be constructed by a single primary, these descriptions cannot be stored in the primary proper. Working with the universal Turing machine in mind, von Neumann introduced an indefinitely extendable linear array, L, on which the description of any secondary or a series of secondaries can be stored. Thus, the primary constructing automaton will consist of a finite part plus an indefinitely extendable linear array, L. The linear array L could also serve as an indefinitely extendable tape for a Turing machine if the finite automaton part, the head, of a Turing machine could be embedded in the cellular structure. By the end of this, question B had been fully answered affirmatively. Moreover, question A as applied to von Neumann's cellular structure has also been answered affirmatively. Von Neumann reduced questions C and D to question B. He reduced question C to B by outlining a plan for converting the primary, constructing automaton into a universal constructor. Von Neumann then reduced question D to question C by showing how to make the universal constructor reproduce itself. In essence, he accomplished this by placing a description of the universal constructor on its own tape L. Von Neumann also designed the universal constructor so that it uses the information on L twice, once to construct a secondary and once to make a copy of L which is attached to the secondary. Hence, a self-reproducing automaton can be embedded in von Neumann's 29-state cellular structure. Additionally, there can be embedded in von Neumann's cellular structure an automaton which can perform the computations of a universal Turing machine and can also reproduce itself. These embeddings require an indefinitely extendable tape and its control inside the infinite cellular structure. The following units were involved in the tape and its control: a linear array L for storing information, a connecting loop C1 for reading an arbitrary cell, a timing loop C2 used in modifying the length of the connecting loop C1, a memory control MC used to control the operations of L, C1 and C2, the constructing unit CU which controls MC. The primary purpose of CU is to carry out the construction of a secondary automaton whose description is stored in L. Thus, the universal constructing automaton has two parts: the constructing unit CU and an arbitrarily large memory and its control MC, L, C1 and C2. The most important parts of the MC are the read-write erase unit RWE and its control RWEC. With that, von Neumann's work terminated abruptly, and he never got to consider in detail question E, evolution. He had stated in an earlier lecture, however, that complication in both artificial and natural automata is degenerative below a certain minimum level, and when that level is reached, the automaton can increase in complexity. This happens through an inheritable mutation, which von Neumann presents in the following manner. To an automaton X, which consists of the reproductive machinery, we can attach another automaton A, so that X plus A plus phi of X plus A reproduces itself. This is the normal function of an autoreproductive organism. It creates byproducts in addition to reproducing itself. The system X plus A can undergo processes similar to the process of mutation. By a mutation is meant simply a random change of one element anywhere. If an element is changed at random in one of the automata, the system will usually not completely reproduce itself. Such a mutation is lethal. If there is a change in the description, the system will produce not itself, but a modification of itself. Whether the next generation can produce anything or not depends on where the change is. If the change is in X, the next generation will be sterile. If the change occurs in A, the system with the mutation is exactly like the original system, except that A has been replaced by A prime. This system can reproduce itself, but its byproduct will be A prime rather than A. This is the normal pattern of an inheritable mutation. Before we proceed, there are three other models of self-reproduction which von Neumann considered and I didn't explain. The excitation threshold fatigue model of self-reproduction was to be based on the cellular model. Von Neumann's idea was to construct the 29-state automaton out of neuron-like elements. An idealized neuron has a designated threshold and a designated refractory period or fatigue. If a neuron is not fatigued, it becomes excited whenever the number of active inputs equals or exceeds its threshold. When the neuron becomes excited, two things happen. It emits an output signal after a specified delay, and the refractory period begins. When an excitation threshold fatigue neuron becomes excited, it must remember this fact for the length of the refractory period and use this information to prevent input stimuli from having their normal effect on itself. Hence, this kind of neuron combines switching, delay of output, and an internal memory with feedback to control the effect of incoming signals. The fourth model of self-reproduction which von Neumann considered was a continuous model. He planned to base this on a system of simultaneous nonlinear partial differential equations of the type which govern diffusion processes in a fluid. All the essential properties of the self-reproducing system must be represented in the equations by functions or dependent variables. Von Neumann probably thought of the differential equations of self-reproduction in connection with his proposed excitation threshold fatigue model. Assume that the cellular model is reduced to the excitation threshold fatigue model. The task then becomes that of formulating the differential equations governing the excitation, threshold, and fatigue properties of a neuron. The plan for constructing the continuous model starts with a discrete system and then proceeds to a continuous one. The transition rule of the cellular model is also the difference equation version of the system of partial differential equations of the continuous model. Von Neumann's continuous model of self-reproduction should also be compared with some work of Turing. In The Chemical Basis of Morphogenesis, Turing analyzed morphogenesis by solving differential equations which describe the interaction, generation, and diffusion of chemical substances. Von Neumann's probabilistic logic and the synthesis of reliable organisms from unreliable components is the first work on probabilistic automata, that is, automata in which the transitions between states are probabilistic rather than deterministic. Whenever he discussed self-reproduction, he mentioned mutations as random changes of elements. He posed the problems of modeling evolutionary processes in the framework of automata theory, of quantizing natural selection, and of explaining how highly efficient, complex, powerful automata can evolve from inefficient, simple, weak automata. A complete solution to these problems would give us a probabilistic model of self-reproduction and evolution. Von Neumann's work on self-reproducing machines has inspired countless simulations of cellular automata and has to an extent predicted the basic structure of DNA. The purely combinatorial aspect of self-reproduction might have been demonstrated by the cellular automata simulations even in von Neumann's time, but we wouldn't see a true kinematic self-reproducer being built, at least not after von Neumann's death. At the turn of the 21st century, we possessed something resembling the universal constructor. The 3D printer. 3D printers back then were almost as large as some of the computers in von Neumann's time, and yet the modern desktop 3D printer is as small and compact as a desktop computer nowadays. We can thank Adrian Boyer for that, an engineer and mathematician who had noticed the resemblance between the 3D printer and von Neumann's universal constructor, and similar to him had wondered, what would happen if I make the universal constructor reproduce itself? Thus, he redesigned the 3D printer to be able to do precisely that. He wanted to have a design whose parts, or at least most of the parts, can be printed on another 3D printer. This was the open source project called RepRap. It achieved the remarkable thing of getting the cost of a 3D printer from around $5,000 to about $500. RepRap operates on the basic philosophy that, similar to how humans have employed artificial selection over the breeding of plant and animal species, they can do the same with a general-purpose manufacturing machine, which, similar to plants and animals, can produce useful byproducts in addition to reproducing itself. This allows for a type of human-machine symbiosis similar to that found between bees and flowers. The flowers produce nectar for the bees, and in return, the bees help the flowers reproduce. It's important to know that RepRap is by far not the only approach for building a self-reproducing machine. For example, MIT's director of the Center for Bits and Atoms, Neil Gershenfeld, is developing an approach with his students which uses identical robotic subunits called voxels that can self-assemble into a rudimentary robot and then collect more voxels to assemble larger structures or even more robots. Voxels are the volumetric equivalent of a 2D pixel. Each voxel can carry both power and data from one unit to the next. Each robot consists of several voxels connected end-to-end. They use small but powerful magnets to latch onto additional subunits, which they can use to assemble new objects or make themselves larger. Whether we use 3D printing, self-assembling robots, or another totally different way to make a machine fabricate a copy of itself, we see one important feature. With self-reproductive manufacturing, ordinary production, which is linear, can become exponential. The impacts this might have on the economy are still largely unknown. Will such machines working together achieve the cybernetician's dream of a self-organizing factory? We can maybe go beyond that and ask whether such machines as the von Neumann probes, which are self-reproducing spacecraft, can help humanity build the missing space infrastructure and expand to a stellar civilization. Although all these things sound exciting, the power of the universal constructor might first and foremost lie not in engineering and industrial applications, but within the area of theoretical physics. A theory which aims to rewrite the fundamental epistemology of physics has been developed at the University of Oxford since 2012. It's called Constructor theory. Constructor theory is a proposal for a new mode of explanation in fundamental physics in the language of ergodic theory developed by physicists David Deutsch and Chiara Marletto. Constructor theory expresses physical laws exclusively in terms of which physical transformations or tasks are possible versus which are impossible and why. I won't go into detail about it here, but here are a few words. The fundamental elements of the theory are tasks, the abstract specifications of transformations as input-output pairs of attributes which belong to a substrate. A task is impossible if there is a law of physics that forbids it being performed with arbitrarily high accuracy and possible otherwise. When it is possible, a constructor for it can be built, again with arbitrary accuracy and reliability. A constructor in this case is an entity that can cause the task to occur while retaining the ability to cause it again. Examples of constructors include a heat engine or a thermodynamic constructor, a catalyst or a chemical constructor, or a computer program controlling an automated factory, an example of a programmable constructor. And who knows, with all these constructors at play, perhaps the universe itself might be the ultimate universal constructor, eternally crafting its own cosmic game of transformations.